Thanks a lot. So where this came out of was we'd broken into internet land speed record, and this erupted kind of a furor on the NANOG mailing list with remarks like, what am I missing here? There's OC48, OC192, production commercial networks can blow away these speeds on a regular basis. And then somebody else said, I'm going to launch a DAT tape across the parking lot with a spud gun and see if I can achieve 923 megabits a second. I thought it might be interesting to maybe go into a little bit more detail. And so this is, as I say, not to be confused with a rocket-powered sled that traveled at 6,400 miles per hour, I think, to test an ordnance of some kind. So what I want to go through is who did it, what was done, how was it done, what's special about this, who needs it anyway, and then what comes next, and a little bit on where do I find out more. And I'm not going to go into the heavy technical details, so it's mainly just an overview of what we did. So the collaborators were people from Caltech, SLAC, that's Stanford Linux Accelerator Center, Los Alamos, CERN, and then we had other people helping from Argonne at Linda Wincliffe and Starlight. And then there were various ISPs, DataTag, Starlight, TerraGrid, SurfNet, and Cisco, and Level 3 and Intel. And then there was some funding from the DOE, the European Commission, and the National Science Foundation. You can see all the pretty logos that everybody has. So what was done? Well, we set a new TCP land speed record, and the way the Internet2 measures the record is it's the speed of the data transfer times the distance. So it's typically measured in terabit-meters per second. So this one, the record was 10,619 terabit-meters per second. Because it's fairly easy to transmit data over short distances. The difficulty comes when you have a large congestion window with TCP. So the first, in November, we succeeded in doing 8.6 gigabits a second across the US. That was from Baltimore to Sunnyvale. But that was with 10 parallel streams. There are 10 separate CPUs sending to 10 CPUs at the other end. And the Internet land speed record specifies there can only be one CPU at either end. So in that sense, that was not an Internet2 land speed record. At the same time, we sent from Amsterdam to Sunnyvale at 923 megabits a second, and that was using jumbo frames, 9,000 byte frames. Then in Sunnyvale, in February, this time we got Intel 10 gig E NIC cards, and so we had another crack at it. And this time we got 2.38 gigabits a second from Sunnyvale to Geneva, again with jumbo frames. And this is actually about 99% of the available bandwidth that you could put over, since it was a packet over Sonic Link and you got to allow for headers, etc. The little graph that you can see shows you the gigabits per second along the left-hand axis and along the bottom, which is time. And you can see just to the right, it pegs out at roughly 2.36 gigabits a second for over an hour. So that was actually transferring over a terabyte in 1 hour from, in that case, Sunnyvale to Geneva. So how was it done? Well, at Sunnyvale, in the Level 3 gateway, we had a GSR router, which was kindly loaned to us by Cisco. We had a large number of CPUs, 1U and 4U high servers. Some of them were disk servers, some of them were CPU servers. And one of these servers in February had the Intel NIC card in it. Caltech provided the CPUs. And then at Starlight, there was a T640 Juniper router, and then internal to that, a 7609, which then had more CPUs. And then across a data tag link across the Atlantic at 2.5 gigabits a second, which was actually the bottleneck. It's kind of interesting to think of a bottleneck as being 2.5 gigabits a second for an end-to-end transfer, but that's what it was. And then to CERN, where there were, which is in Geneva, Switzerland, where there were more servers. So here's some of the typical components. You can see down at the bottom right, there's the GSR. That's a 12,000 with a 6 CPU, six useful slots in it. the 1U high servers with an earthquake strap around it because it was in California, the disk servers, and the Intel NIC card, which is just, and you can see the size of the card because there's a cent piece sitting on the heatsink. It's kind of interesting to see how big the heatsink. It occupies almost half of the card. We used that for the latter test. The original test we're using Sysconnect NIC cards. So let's see. I think I can skip on to the next one. So what were the challenges in this? Well, there's the PCI bus limitation. 66 megahertz, 64-bit CPU PCI bus can do 4.2 gigabits at best. So we actually, in the latter test, we made sure we had 133 megahertz CPU PCI bus. At 2.5 gigabits a second on 180 millisecond round-trip time, that was to CERN, we needed 120 megabyte windows. So these PCs had to have plenty of memory in them so that they could accommodate that window fairly easily. We ran into some of the tools which we were using for the testing. BBCP, which is a file copy program, wouldn't allow a window bigger than 2 megabytes. So we didn't wind up using that. Slow start at 1 gigabit a second takes about 5 to 6 seconds on 180 millisecond link. So if one wants to measure 90% of the measurement in the stable, that's a non-slow start state, then we need to measure for over 60 seconds. Or if we would need to ship 700 megabytes at a gigabit per second in order to be able to run for that amount of time. So you need a fair amount of disk at both ends. And then, of course, the problem with the standard TCP stack is with its additive increase and multiplicative decrease, that as soon as you hit a loss, it can take a long time to get back up, since you're only adding one packet per act coming back. And you can see that down on the right there. The bottom scale is 0 to 1,000 seconds, and you can see it only goes from about 450 to about 620 megabits in 1,000 seconds. So it takes a long time. So you're very sensitive to any loss. This is a test circuit, so there wasn't much loss, but any loss certainly would back us down quite a lot. So in terms of what was special, it wasn't just measuring the speed on the backbone with a lot of aggregated links. It was actually an end-to-end application, one CPU at one end, one CPU at the other end. We actually did try with multiple streams and single streams, but we were able to actually get good performance just using a single stream. It also illustrates quite nicely that even though TCP was designed for a 56 kilobit per second network, it actually has not run out of steam yet. It actually scales up to the multi-gigabits per second region. And TCP is nice in the sense there are other protocols which you can use for transmitting data, some of which are based on UDP. The nice thing about TCP is it's well understood, it's mature, it's got a lot of nice features, reliability, and it's friendly to other users of the network. We also looked at some new TCP stacks. There's at least 3 out there at the moment. One from Sally Floyd called High-Speed TCP, another one from the Cambridge University in England called Scalable TCP, and a third one from Stephen Lowe at Caltech called Fast TCP. These all get around the problem that the additive increase and enable you to actually recover much quicker after losses. They worked very nicely, and the nice thing about all these TCP stacks is they only need to be deployed at the sender. They don't have to be deployed at both ends. And all the and in that case, we were able to get good performance and not need the jumbo frames. If we used the standard TCP, we had to use jumbo frames. So we used commercial off-the-shelf hardware and software. There was no special equipment here. I think in terms of importance to others, I mean, it raises the bar on expectations for applications and users, and I'll come to some examples of applications that need these speeds. Some applications can actually use them, and so they actually provide planning information for people who want to think about whether or not they should be shipping truckloads of data around the world, or 747's worth of data around the world, or whether or not they can actually use the internet to do it. And the network is now, with these kinds of speeds, the network is beginning to exceed the speed of which you can accept that amount of data into a PC. And the PC increases in performance are not happening as fast as the network speeds have been happening in the past. So it's looking much less like the network is the bottleneck, but rather it's it becomes a catalyst and enabler, and the bottleneck has moved somewhere else to the PCs itself. In terms of shipping data around the world, we certainly in high energy physics, that's my own field, used to ship data via 747s from SLAC to places in Europe. And the best you could do, assuming that the plane didn't have any delays or anything like that, would be about 10 hours. And if you had a fully loaded 747 and it took 10 hours to get from, say, San Francisco to Geneva, then that's roughly 2 to 4 terabits a second. And actually that's not fair, because you then have to unload the tapes, you have to get off the plane, you have to get them through customs and everything else like that. So actually the turnaround is closer to 2 weeks. So who needs it? Well, as I mentioned, our field, that's high energy physics, need it, because we're receiving from our equipment roughly 50 megabytes a second, and we need to transfer multi-terabyte files per day across the Atlantic. And we're doing that, and actually we already have databases which are about well over 3/4 of a petabyte. And that's doubling at roughly each year, so that in a decade we expect to be getting close to an exabyte. The other sciences that need this are in particular data-intensive sciences such as astrophysics, global weather, bioinformatics, the human genome, fusion and seismology. And then industries such as aerospace and medicine. Particularly the radiation oncology people. When a patient visits goes for a visit to a hospital, typically they will create pictures like mammograms, where there's 2 breasts taken from 2 views. That typically comes out to be 100 to 500 megabytes per visit. And there's thousands of visits, especially around the world. So they already, in the UK alone, they already have 400 terabytes of data, which once you can start sharing that data, you can start mining it and looking for new ways to treat patients, new commonalities between what's going on and everything. So I think that there could be big improvements in patient care and things like this as one begins to get these speeds. Obviously, in the future, media distribution becomes very interesting. At a gigabit per second, that's roughly 2 full-length DVD movies, 2 full-length Matrix Reloaded in 1 minute. When you can do that, you kind of have to wonder what Blockbuster's business model becomes. At 2.36 gigabits, that's roughly 200 full-length DVD movies in an hour. And you kind of have to wonder whether sharing movies will be like just sharing music is today, which will kind of be interesting to see what happens. Maybe the internet will then become full of, somebody I think put it on the list of cease and desist notices, many, many pages long from the lawyers saying don't do this. When will it have an impact? Well, this is kind of, I'm trying to get a handle on this. The top left graph shows you the amount of traffic. How am I doing? Oh, all right. All right. Shows the amount of traffic you're getting on ESNet. It's roughly doubling per year. The next graph down shows the capacity at SLAC, which has been increasing by 90% each year. If you take what's available in industries today and you double them at these kind of rates, then a firm which has 622 megabits today will have 10 gigabits in 3.5 to 5 years. And we can expect similar increases to many other places. The question of the home is interesting. There is an initiative in California to try and get 1 gigabit to the home and to industry within the next 10 years. Whether or not that will happen, I don't know, but that could mean these speeds will be very important. Okay, I'll skip that. Okay, what's next? We want to beat the 2.5 gigabit per second link. We want to do disk to disk. This was memory to memory, so it's not really useful to most applications. We want to evaluate new stacks. We want to understand how to make the 10 gig NICs work well with 1500 byte MTUs. Though we made lots of tests, we did not succeed in all the tests we wanted to do. And I think the big thing is to move these from hero demonstrations to the commonplace. In our case, we had 24 people working round the clock who were pretty much wizards in their own areas. I mean, not each person didn't work 24 hours, but because there were people in Geneva and things like that. And still, we did not manage within the week that we had the 10 gig cards to do all the tests we wanted to do. So it's fairly complex today. So there's some a little bit more in case you want a bit more information. There's some URLs there.
Question? Or should I shut up and sit down? Okay. There's a clearly established methodology for testing world land speed records since the 1950s, and this does require the average of a bidirectional test. You have to run the car in both directions across the fault line. Are you planning on doing this anytime soon?
I haven't seen that standard, but it would be fairly easy to do.
Specifically, the test is the average of 2 runs in each direction within an hour.
Okay, do they run for an hour? Or just...
Well, the cars don't. The cars only run for a few seconds.
Yeah,
but
okay, no, that would be pretty easy for us to do. We didn't do that, though.
Let's face it, there's a lot of water between CERN and SLAC. This isn't the land speed record at all.
Hi, Avi Friedman. I haven't followed the whole thread, but one of the things that some of the people in the commercial internet space, internet measurement space, did that I thought was interesting was they started measuring not milliseconds, but milliseconds per mile. And I think one of the interesting ways to calibrate some of this is, as you point out, it's much more challenging to get higher speed, the more distance you have. I think it'd be interesting to start looking at reporting measurements in terms of milliseconds per mile or throughput per unit distance. I think that would also be interesting when someone says, well, I got the DAT drives shot across the parking lot versus...
We just lost 5 minutes of lunch, boys and girls.
30 seconds, but not 10.
So what do you want from ISPs other than faster links and faster interfaces? Should the ISPs do anything differently to enable this? Or is this all end system code?
I think what we want from ISPs is this to become, we just want this to become commonplace. We want it to be available, we want it to be available at a price that's affordable.
Available in terms of faster links, but nothing else that we have to do.
Moved end packets.
Thank you.
Oh, but yeah, jumbo frames.